graphing rational functions. So we've talked about our excluded values in a rational function, those values that make the denominator equal to 0. Those also affect our graphs of rational functions a little bit. So let's take a look at what a graph of a rational function looks like. So a rational function can be described by an equation y equals p over q, where p and q are polynomials, and q cannot be equal to 0. So again, we can't have a denominator equal to 0. The parent function. So this is kind of the basic function of a rational function. If we're going to look at just where we kind of start from, f of x equals 1 over x. That's our basic. Doesn't get any simpler than that as far as a rational function. The type of graph, it's a hyperbola, and that's our kind of water slide roller coaster slope here. It's not a slope, it's kind of a curve to it. The domain, we're going to have to be excluding something. So our domain is going to be x such that x doesn't equal whatever our excluded values are. And our range is y such that y doesn't equal whatever our excluded values are. So again, we're looking to see what values can I not include in the domain or the range to be able to graph this. So because excluded values are undefined, they affect the graph of the function. An asymptote, here's a new word for you. An asymptote is a line that the graph of a function approaches. So you'll notice again, if we think of this like a water slide here, this line kind of approaches the x-axis, but it never actually gets quite near it. And we talked about this a little bit when we were graphing our inverse variations. So again, if we talk about inverse variation where x times y equals your constant, we can't have x or y be equal to 0. So this graph gets closer and closer and closer to the x-axis, but never actually touches it. It can't actually be 0. So in this particular case, which is why we have can't be equal to 0 here, it's not actually equal to 0. So when it says it approaches that line, it gets closer and closer and closer, but it never actually touches whatever that asymptote in here is here. And the asymptote can move. For the ones we've been working with, we've worked on those asymptotes really being the x and the y axis, but they can be anywhere in the graph depending on the function itself. So a rational function in the form of y equals a over x minus b equals c has a vertical asymptote, so our vertical asymptote, at the x value that makes the denominator equal to 0, which if it's x minus b equals 0, add b to both sides, x equals b. So this is going to be your vertical asymptote. It has a horizontal asymptote at y equals c. So again, if we recognize that what happens in here makes this whole equation equal to 0, makes this, not this whole equation, but this whole fraction here equal to 0, then y would not be, we couldn't have y be equal to c, because that would be our horizontal asymptote. Let's see what this looks like when we actually start to work with an equation. So what are we going to do to graph a rational function? 2 steps. First step, identify and graph the asymptotes using dashed lines. So those are going to be kind of our borders. The asymptotes are going to be, you're going to get close to this with your hyperbola, but not ever actually touch that line. Our vertical asymptote is x equals b, and remember your equation, your denominator is x minus b. Your horizontal asymptote is y equals c. So make a table of values and plot the points that connect them. That's our second step. Identify the asymptotes of each function, and then graph the function. So we're going to follow these 2 steps to graph this particular function. So y equals 2 over x minus 3 minus x plus 3 minus 1. So remember that the parent equation for this is x minus b here in my denominator. So b is actually, since this is plus here, this is x minus a negative b. Again, it's whatever would make this equal to 0. So if you go back to thinking about our excluded functions, it's that excluded function here. So if I said x minus 3 equals 0, well, then x can't be negative 3. X can't be negative 3. There's your vertical asymptote. And our horizontal asymptote is going to be whatever this plus c here is at the back. So y can't be equal to negative 1. So I'm going to start on my graph by graphing those 2 asymptotes. So I'm going to say x equals negative 3. So x equals negative 3, and I'm going to make a vertical line there. And that's, again, kind of a boundary. It's been up until now kind of the axes, but for now it doesn't need to stay on the axes. It can be anywhere on that coordinate plane. My y equals negative 1. I'm going to come down here to y equals negative 1, and I'm going to give myself a vertical line. So again, these are my boundaries of my hyperbola. I don't know where they lie on the coordinate plane yet. I'm going to have to make a table to figure that out, but this at least gives me an idea of where this graph is going to sit on my coordinate plane. So now I'm going to pick some values of x for my domain that approach this vertical asymptote of -3. So I'm going to start with numbers less than a -3. I don't have a huge coordinate plane here, so I started at -5 because that's kind of as small as I went. I could have done -6 or negative whatever made it easy. I did pick integers that were friendly with this particular expression though. So I threw a -5 in there. -5 plus 3 gives me -2. 2 divided by -2 is -1. -1 minus 1 is -2. I threw a -4 in there. -4 plus 3 gives me -1. 2 divided by -1 is -1, is -2. -2 minus 1 gives me -3. I plugged a -2 in there. That gave me 1. 2 divided by 1 is 2. 2 minus 1 gives me 1. Notice I skipped -3. And I skipped -3 because that is my excluded value. If I put -3 in here, I get 0 in my denominator. So I skipped it. So now we're on the other side of the line here, -2, and I plugged in some other values to give me an input and an output. So let's graph those. So -5, -2 is down here, and -4, -3 is down here. Now I'm recognizing that my hyperbola is going to be in this lower left-hand corner. I know that my hyperbola is going to approach each of these asymptotes, so I can kind of flesh in what that graph is going to look like. It needs to go through these 2 points, so I've attached them to those 2 points, but then I've made my line approach each of those asymptotes. So it's going to be in the curve here, and I've kind of given these 2 points as kind of where I know that it's going to be in that corner there. So I know it's not going to be way deep in this corner. I know it's not going to be really far out. It's going to sit right there. Then I plotted the rest of my points here that I had, and I did the same thing. I know that my hyperbola is going to approach this asymptote here, so I made that curve fit the points that I already had, and then I know that the other side of my hyperbola is going to approach this horizontal asymptote down here, so I kind of made it fit that. Again, the line that you're drawing should not connect to the asymptote. It should just come right along it. Just kind of ride right next to it. Kind of like if you think about the ground as you come to the end of the roller coaster. You're in the car there, so you're never actually touching the ground. You're on the rails, you're in the car, you're coming close, but you're never actually touching it. So when we think about graphing a rational function, this is what it's going to look like.